We sort of took over them.
Okay.
They all have the option.
Like Carl.
TA. Yeah, really, right?
Oh, yeah.
Which paper? Outlet.
Okay, does that work? I think it does.
Either way.
I don't, is this, yes? Okay, thank you everyone for coming back for the rest of this morning's session. So we're going to start off with Charles Prophet here, but I did just want to say thank you for bearing with us with the technical difficulties. This is the first conference that we've done in this room since the technology upgrade, so thank you all for your patience, and we will hopefully get the worked out later today. Go ahead, Charles.
Okay, so I'm going to just try to give you an update today on where we are with the new spec FLUX calibration. And in some places, I'm going to emphasize the results you can get out with a little bit of massaging. So the pipeline isn't yet always doing this well, but we'll be trying to fix that. There's been a very large number of people who contributed to this. The names up here on the slide are just some of the more recent ones. I mean, the whole IDT, NeoSpec IDT, many members of which have now moved on back to Europe, also made very substantial contributions here. So since not everyone's familiar with NeoSpec, I just thought I'd give a very quick overview of what NeoSpec does. It's the near-infrared spectrograph on the James Webb Space Telescope. It covers from about 0.6 to 5.3 microns. It has 6 different gradings with, in 3 bands. The high-resolution band has nominal resolution of around 2700, the low medium resolution band of 1000, and then there's the prism, which is much lower resolution, but because you don't have to worry about higher order spectrum in the prism, you get to cover the full wavelength range rather than just a factor of 2 or so in wavelength. And on the shortest wavelength band, you actually get a choice of 2 long pass filters if you want to tweak the wavelength range a little bit. And there's a number of ways you can use these gratings with the instrument. The sort of signature mode is the multi-object spectroscopy, where you get where you have about 2.5 million microshutters. You can select which microshutters you want to open and point the telescope to get tens or dozens or sometimes up to 100 different targets getting simultaneous spectra. In addition, there's an integral field unit which just does a much smaller 3x3 arcsecond area, but then slices it into 30 10th arcsecond wide slices. And each slice projects onto a different area of the detectors. So you can build 3D data cubes from that. In addition, there is the fixed slit spectroscopy, which is some fixed slits in the same sort of the same optical chain as MOS, but you use some predefined fixed slits instead. And then there's the bright object time series, which optically and onboard the spacecraft, it's really fixed slit mode, but the onboard execution and data processing is optimized for taking very long time series, where you want very precise relative photometry for things like transiting planets or whatnot. But in terms of absolute flux calibration, well, I'm not going to really distinguish between that and the fixed slits. And there's just an idea of the geometry. There are two detectors and these 4 microshutter quads, and again, the programmable microshutter cards. The fixed slits in between is the IFU aperture. Another thing to know about the geometry is that the prism and the medium resolution spectra, the useful ranges are short enough to fit on 1 detector. In fact, for most of the fixed slits, they'll always be on the NRS1 detector. While for the high dispersion, most of the modes are long enough that you have to split them between the 2 detectors with a wavelength gap. Another thing you have to keep in mind, though, is the original calibration concept divided the detector into essentially the detector, the spectrograph, and the 4 optics. And that in principle, there's a separate set of reference files, both pixel by pixel and throughput versus wavelength for each of these sections. However, most of those have to be either theoretically calculated or done from ground-based measurements, some of which can't be repeated on orbit in practice. For example, once we put the micro shutter plate in front of the detectors, you really can't do a uniform detector flat field. You only can do flat fields through the micro shutters and through the optics. So in practice, when we adjust the on-orbit calibration, what that means is we have these internal lamp exposures, which can be used to update the 2D pixel by pixel flats in the so-called spectrograph or S-flat region. And then we use external targets to update the 1D wavelength dependent part, which is assigned to the 4-optics flat. But in practice, each of those on-orbit corrections, if there are any mistakes or errors or sins in the other parts of the flat fields, we'll be fixing them when we do that with these two on-orbit calibrations. And one problem of that is, of course, it tends to be then, if you're fixing up a field-dependent problem with the 4-optics flat, it's going to be very sensitive to, you'll need to do it separately for each aperture in principle. And so that does complicate doing the absolute calibration. Now, Carl mentioned that repeatability is important. So before I discuss absolute flux accuracy, I'm going to briefly discuss the repeatability. And if you do exactly the same thing in exactly the same way, you can get extraordinarily good repeatability. For our sort of monthly monitor, which we do with just the one G140H grading, if you just take a big band, two big bands, one for each, the half of the spectrum that falls in each detector, and just do the repeatability, the RMS variation of those broadbands is only about 0.2%. So that's extraordinarily good. And if you look at the pixel-to-pixel level, and when you reject the worst outliers, it comes to maybe 0.6% RMS. And that, you have to do some special things with the processing. For example, this when we turned off used the bright star, turned off the background subtraction, and ignored the dithers that were too close to the edge of the aperture just to get this kind of result. And an example on the right is if we observe this, one of these, the star we observe intensively every cycle is the G star P3030E, and this is simply taking the extracted spectrum from the cycle 1, from cycle 2, and dividing by the same thing from cycle 1, just again doing the same tricks with the background and the dither positions and ignoring the background here for the moment. And as you can see, we get everything, the systematics are far less than 1%, and there's no real sense of any real time change that we want to believe. So that's very good. The IFU mode's a little bit trickier, since you're putting these things in the shutters and you projecting things to different parts of the detector. In fact, between these two observations, we actually changed the pointing so that we're not we shuffled around the slices a bit. So, and that can be from slice, depending exactly where you put in the IFU, there can be differences of the order of a few percent based on both exactly where you land in an individual slice and what part of the detector you're projecting on. But even now with this, you averaging over the this is taking 4-point nod pattern and averaging over the 4-point nods, you get to within 1% or so repeatability without any extraordinary effort. And if you were to more precisely repeat exactly the same observation, you might do a bit better there. Okay. Now this is a list of the standards that we've observed so far of NearSpec. Not complete, but pretty much most. Most of these were described by Carl as part of the program, that the cross-instrument observing program. There was a few extra A stars in here that I think were added by a geo program from the SphereX team, because they wanted some extra A star calibrators, and those are somewhat useful here, although I won't discuss them much. And the green is the A stars, the pink is the G stars, and the blue is the, in this case, they're white dwarfs for us, the hot stars. One thing to note, though, is that the calibration source we use is, not the perfect calibration source, but it's some ways, many of the modes were really only observed with the original commissioning calibration source. And with some fill-ins from another A star. And the other thing is to note is that for the fixed slit, we can use small subarrays, which means we can get a big dynamic range. So we can observe even bright stars with the prism, which is this low dispersion. But if we go, for example, the MOS and the IFU mode require full frame detector readouts, which are rather long. So if you observe these bright stars with the prism in those modes, you just saturate right away. So to calibrate the full frame IFU and MOS mode, we have to use fainter stars. In this case, for commissioning, it was primarily done with this G-star Snap 2. And we also have this additional data for this somewhat fainter G-star, G31, because Snap 2 was actually a little bit too bright, and you got maybe one or two groups before it saturated in some of these modes. And just the ones outlined in the orange are the 3 stars, which we did intensively. And so those are the ones I'm going to compare in the next slide. Some issues, though, that prevent the pipeline for the moment from doing quite as well as I'm going to show you is that most of our stars have been observed in the S1600A1, which is a short but wide square aperture. And it's actually a little bit too short. And so when you dither in that, there's quite a bit overlap of the PSF at the different dither positions. And if you then try to subtract each other from backgrounds, the amount you subtract some source, and it's going to depend on the dither spacing. Now, if we only supported one dither pattern, we could just build that into the calibration. But we have 5-point dithers, 3-point dithers, and each of those adds possibility of spatial sub-dithers. And plus there's bots mode, which doesn't dither at all. So at the moment, this is kind of effects you can get of a few percent, depending on how you handle the dither pattern. And so at the moment, the pipeline doesn't necessarily correct for this at all. So you'll get results that vary. In fact, some of the older versions of the pipeline, they subtract dithers too close to each other and get 20% errors. But we're fixing that. Another thing is that the repeatability, the prism in particular is subject to corrections for small pointing, it's more sensitive to small wavelength misalignments. And so that's maybe we're only doing 1% because of that in the different slits. And there's a bit of an issue with the S200A1 when we change the pointing position. We haven't yet fully calibrated it out the difference in the slit centering. So there's some errors in there we have to fix there in the pipeline. And the repeatability probably won't ever be quite as good there. But here on the left, we show for those X1600A1 observations for those same 3 bright standards using FLUX that were scaled to match the target used in commissioning. So I'm not showing that one here because that one's defined to be unity. I'm plotting here for clarity. I'm doing some smoothing of the results, so I'm not showing the pixel-to-pixel variations. But you can see that the solid lines are the high dispersion modes. The dotted lines are I think I got that right. Yeah, the dotted lines are the medium resolution modes, and the little dotted dark line is the prism. So for a given star from the different gradings agree to within 1%, which is good. The prism is sometimes off a little bit more for reasons we have yet to completely understand, although on these bright stars, the prism is starting to get towards the top of the full well, so that may be some linearity issues there. On the right, I show the same 3 stars observed with the IFU. This is using a 4-point knotting pattern where we actually do the background subtraction. We're just using the 4-point knotting pattern. And these aren't quite the current pipeline products, but once we update the FLUX, you should be able to do close to this, as good as this. As you can see, if you can read the numbers, which I guess are a little bit small there, that for the most part, everything is pretty much within 2% right now. Once you have to do some tricks with correcting for the knotting overlap in the S1600A1, which aren't in the pipeline yet. But once you do those kind of things, we do get everything within about 2% and 1% consistency for stars. Now, this slide I just snuck in the last moment because we got some new data last night. And the top is just an illustration of the different, all the CalSpec models plotted in this lambda squared times F nu space, just so you can see the dynamic range we're getting. And the brightest calibrated stars we use are ones in around a few times 10 to the minus 2, while some of the fainter ones are in around, in this plot, around the 10 to the minus 3 or a few times 10 to the minus 3 level. However, recently, as part of the new program, there's some fainter white dwarf standards that Axelrod proposed, which are those down in the bottom near the 10 to the minus 4 level. And just last week, we got our first couple of observations of these. So in the bottom plot, I'm simply dividing again, doing my tricks for the processing and then just dividing each of those spectra by the CalSpec model. And this is just for the white dwarf observations. Now, the DB star has some issues with the model atmosphere, which is why it doesn't agree, why it's low on the old one's low. But the other white dwarf stars, including the new faint axolotl ones, actually agree remarkably well with each other. And they actually agree with each other better than they agree with overall calibration. And at the red end, the axolotl stars aren't very, Okay, so I'm running out of time here, and I still have the Mars to discuss. On the lower left there, that's sort of the, in addition to the Mars calibration, which has some issues, which we were going to improve in the next cycles, we also did a field where we took this faint OG star and sampled it at 10 different positions over the field of view. And so at the moment, there you can see there's some field dependence differences. We hope to improve that once we get some better handling of the geometric and wavelength distortions in the future cycle. But as you can see, as it is now, the overall calibration is better than 5%, and the field-to-field variation, the field dependence appears to be less than 4%. And although, I mean, here we put the stars exactly at the center of each shutter, so that doesn't include uncertainties from the flux of the shutter placements. And we're going to be redoing the Mars FLUX with white dwarf standards. As you see, I think this pretty much summarizes things. Overall, we're good to within 2% for the IFU and the white dwarf figures as soon as we make a few pipeline improvements. And the other things are good to within 5%, but we have more work to do on some of those.
Thank you, Charles. Do we have any online questions? No? Okay. So I have been asked to carry the microphone to you because others in this room cannot hear. So are there any questions here in the room for Charles?
So the $1 million question, Charles, about the steps that are not currently implemented in the pipeline to get this 2% accuracy. So the first one, when is that you think going to become available to users? And then the second one, can you expand a little bit more on what kind of improvements those are?
Well, I think to the extent we're updating the FLUX, that should be available in the next few months. How to handle the overlap, especially for the S1600A1, where you have such a big overlap in the PSF, how to get the pipeline to handle that is a little trickier, and we're discussing with the software folks when and how to implement that. And it works best if you use a custom dither correction for the exact dither pattern you used, based on observing a bright star and then doing it with and without the background subtraction. But of course, we don't have observing time to observe every possible dither pattern with every possible star. So the correction, we have a generic correction that's a little less accurate. That's maybe another couple % variation depending on exactly how. So we're still discussing with the pipeline folks how to get the pipeline for the fixed slits to do the thing on automate. For the longer fixed slits, the overlap's pretty small, so that's going to be less of an issue.
Thank you. Are there further questions?
Just to follow up on that, then, is there a list then of the dither patterns that you actually have good standards for, so that we which to use?
For the observations, we mostly use the plain 5-point dither in the S1600A1 and the plain 3-point dither. There are some other sub-dithers we have in spectral direction, but that shouldn't affect the overlap too much. So in principle, we could, for those, we can publish a list of the correction factor. But I guess if you're doing the spectral sub-dither, the spatial sub-dithers, then it gets a little more complicated to do it right. And plus another issue with the S1600A1, the top and bottom dithers are getting a little close to the edge of the aperture. And so if your pointing's a little bit off, they won't do so good for absolute flux calibration. And there's also some vignetting in the S-flat. So for these comparisons, I just use the upper and lower nods for background when I needed them, and just use the central 3 dithers to push the absolute flux calibration as high as possible.
Okay, further questions? Any comments online? Okay, great. Thank you, Charles. Okay. So I'd like to welcome Martha Boyer. And
Okay.
I'll
Can
get
you
the
hear me
timer
okay?
started. As soon as I get the timer started, you may start.
Oh, okay. I'll wait. Okay. All right, so I'm Martha Boyer. I am the branch manager for the NearCam team, and I'm going to just give you an update on the status of the NearCam FLUX calibration. So first, a quick overview of the NearCam instrument. We have 10 detectors. 2 of them are long wave and 8 of them are short wave. And we have 2 modules, and that's because NearCam is actually 2 instruments bolted back together. They're mirror images of each other bolted back to back, and each one gives us one of the modules. And each module has 5 detectors total. We've got a shortwave channel and a long wavelength channel that get the same field of view. And we have 5 observing modes: imaging, coronography, time series, imaging, GRISM time series, and wide field spectroscopy. And NearCam has a lot to calibrate. It seems, it's just a simple imager, right? It seems to be easy, right? But it has a ton of elements. And first, we've got 29 filters split between the 2 channels. We've got 4 GRISMs, 2 on each module. They disperse along the rows and on the columns. We now have a short wavelength GRISM, which is using the DHS from commissioning. And that hasn't been calibrated yet. That's brand new. But I just threw it up here just to show you that it's coming. We also have weak lenses that disperse the flux over many pixels so you can observe bright targets that we have to calibrate. And we have 5 coronographic masks, 3 round and 2 bars. And they can all these things, the GRISMs and the masks and the weak lenses, can all be paired with any combination of those filters, right? So there's a lot to calibrate here. And I'm going to describe where we are. So you may remember in the early days there was some kerfuffle about the NearCam calibration. So let me just describe what happened there. The calibration turned out to not be great at the very beginning, and that is because from commissioning we didn't have a full set of calibration data yet, and that's just because there wasn't time. So we had to compromise, and what we did was we put 1 star P330E on every filter and GRISM combination on just 1 detector. And then we looked at the LMC to then transfer that flux to all the rest of the detectors. And the community started to notice right away that it wasn't really working that well. And then when one of the ERS programs observed a globular cluster, it became really obvious that there was a problem. This is M92 from the Stellar Populations ERS program, and we're seeing multiple main sequences that shouldn't be there, and that is from all the different detectors in NearCam, right? And so this was a problem, and basically we dropped everything to get this fixed, and we pulled a whole bunch of the calibration observations forward so that we could do it quickly. And that is what I'm going to show you today. And you might remember there was a bunch of press about this. There was a panic from the community. Everybody had to, go back and look at their papers and rethink some of their conclusions. But we've got it all looking good now. So let me describe what the Cycle 1 calibration program looks like. This is a much more thorough program. This is 3 primary stars, a G-type, an A-type, and a white dwarf, that were observed on every single detector, every single filter, every mask, every GRISM, everything that you can think of with NearCam. And then we also have a bunch of secondary targets, 2 A-type, 2 white dwarfs, 1 G-type. And then we also actually observed a cluster with a bunch of G-type standards, but Everett Schlauman's going to give a talk about that later in the week, so I'm not going to talk about that. But those stars, the secondary stars, were just observed in a subset of the filters, only 5 filter pairs, just to sort of have an extra check. And I'm showing just what the PSF looks like on NearCam. The top ones are imaging, short and long wavelength. The ones below that are the round masks from coronography. The ones below that are the long masks, or the bar masks, sorry. And below that are the weak lenses, showing how the flux disperses. All right, so we did just basic standard procedure here, nothing too fancy. We did aperture photometry, threw out bad dithers that had too many bad pixels. We used WebPSF to do aperture corrections. We're using CalSpec to convert to physical units. And we calculated a calibration factor for each individual target, and then averaged all those together to get the final calibration factor, which is the FOAT-MJSR keyword in your headers. And this is all in the pipeline right now, by the way, what I'm going to show you. So here are the results for imaging. This is just one of the filters in each channel. So it's the module B, 4 detectors in module B for FO70W. And then the one on the right is the long wavelength one for 356W, and that's on also module B. And you can see this is one of the ones that had the extra secondary targets, so it's more than just the 3 targets. And you can see just how nice and flat they are. It's zoomed way in, so it looks like a lot of scatter, but it's not a lot of scatter. And if you squint, there are these little percentages up in the corner that are all less than 1%. And that's how almost every filter is in almost every detector. There's a couple that are between 1% and 2%, and then there's a handful, just I think 4, that get above that. The worst one is 3%. But altogether, it looks good. There's no obvious trends with the source flux. And NearCam is looking really great. I wanted to point out that all of these observations were taken on subarrays. So we had to look at the differences in flux measurements between the subarrays and the full frame. And that's what we're showing here. This is just a sample of them. And what we did here was we took a star, put it on the detector, in the same spot on the detector, and observed it in the subarray and the full frame and compared the fluxes. And most of them look like this guy over here. Where it's just flat as a pancake. They look fantastic, way less than 1%. There's a couple, or there's one actually, that looks like this, where the dithers have a lot of scatter, but the average is good. And then there's one over here where there is a little bit of a trend. All the dithers agree that there is maybe about 2% of a difference here for this particular subarray. But it's all small. This is the worst one, about 2%. So this is contributing a little bit to the uncertainties here, but I just wanted to point out that it's not in the current pipeline. It's going to be in the next delivery. So here's just a figure showing a summary of the imaging, and this was delivered last September. And what I'm showing here are the 3 primary calibrators, and then the mean, and then the previous value. And you can see that it's really tight. There's basically no scatter for any of these filters. This is just one, this is B4 and this is A long. The worst ones are these guys over here, the 430, 460, and 480 medium band filters, and they're around 3 to 4%-ish. I think the worst one is like 3.2% or something like that. But altogether, we're doing really, really well in imaging. And when you go back to that ERS data, they published a paper this summer showing how much nicer it is. And so this is the short wavelength color magnitude diagram, and this is the same one that I showed on that early slide, so it's much, much better now. But if you combine the short wavelength with the long wavelength, they only had a couple filters, and this is their short and long wave combination. There is still a little bit of a bifurcation here. It's teeny, but it's on the order of about 1 or 2%. So you can see it when you're looking at data like this, but it's still very small. And we're tracking down, what exactly happened here, and additional data is going to help push this even lower. All right, so here is just a summary of what we've been delivering to the pipeline for imaging. So that initial delivery is in green for all these filters, and then the one that happened just a couple months later is in cyan, and then the latest one is the dark blue one. And so you can see some of the filters changed quite a bit. And these are all these dots are the different detectors, by the way. There's 8 detectors in the short wavelength channel. So some of them did have pretty big changes, but there wasn't a huge change between last year and the previous year, the cyan and the blue. So it's been pretty constant. And the long wavelength is pretty flat too. All right, so now on to some of the other modes. Here's the summary for choreography. This is which one is this? 335R. So this is one of the round masks. And you can see it's very tight, also just like imaging. We are off pretty far from some of the X's, and that is because that was the pre-launch model data. So that's why it's so different. But the data itself are really nice and tight. The worst one here is the long wavelength bar, and that was a mistake that we made where we failed to account fully for the rotation of the bar in the field. And at one point, it clipped the edge of the stars. And so, for a couple of the filters, the calibration is not great, 12 to 14%. But we're working on fixing that. We've got new data coming in, and we're gonna get that down to 1 or 2%, like everything else. Here is the GRISM data. This is analysis from NorPearsCal, and the FLUX calibration is about 2% compared to CalSpec. But I'm also showing here the trace results and the wavelength results, because you can use all of this together to create a simulation. So the observations are here on the left, the middle are the simulations, and the residuals are on the right, and you can see just how nice and clean they are. So the GRISMs are also looking very good. And then we have a note on stability. This is our the same program that Carl and Charles were talking about, where we're imaging just one star about monthly in just 2 filters, 212N and 470N. This is very, very bright, so we had to use the narrow filters. And we did it on all 10 detectors. And this is the short wavelength on the top and the long wavelength on the bottom. And you can see just how nice and flat it is. So all of these tiny numbers that you can't read, I'll show the scatter. And these are all less than 0.5% here on the short wavelength channel, except for this one's 0.56. So I lied a little bit, but it's close. And then down here on the long wavelength channel, module A is about 1% and module B is 0.7%. So very, very repeatable. And that is it. So the summary for what is currently in the pipeline is that we have less than 1% uncertainties for imaging. This was delivered last fall, and up to 2 to 4% for the worst ones for a couple of filters. The full to subarray transfers are all less than 1% for the most part, except for one bad one that's around 2%. Stability is less than 1%. Coronography, 1.5%. GRISMs, 2%. Basically, we're doing great. And so we're really happy with this. We're analyzing cycle 2 and 3 data right now to incorporate all of this into it. And I also wanted to point out that there are a couple things that are still missing. We don't have the weak lenses in the pipeline yet. And we also don't have, for coronography in channel, or in cycle 2, we started a new mode where you can use a mask in one channel and collect data in the other channel. And we don't have any calibration data for that yet, where you use like a long wavelength mask with a short wavelength filter, right? But we're working on getting that so we can calibrate that as well. And so all of this is going to be part of 2 papers, one on imaging modes and one on GRISM modes from NorPearsCal. And that's it for NIRCam.
Thank you. Are there any questions for Martha? Yes.
Hi, what's the expected timeline for the DHS availability for call for proposals?
It's available. You could have proposed for it in this last
Cycle 4.
Yeah, it's not completely finished yet, so it's sort of a shared risk. But by the time cycle 4 starts, we expect it to be up and running and useful. So.
And calibrated?
And, well, we had to get the data first to calibrate it, right? And so.
I have a request. Can I ask, since I had the mic, 2 seconds. So maybe you said that there's maybe a split still in the M92 sequence. Could it be that it's just intrinsic, or are you sure that it's due to the calibration?
We think it's probably due to the calibration. We're not sure if it's the FLUX calibration or if it's something else in the pipeline, you know, like the flat field or I don't know, whatever. Or it could just be that particular filter has a problem, right? Because that program only got 4 filters, I think. And so in the short wavelength filters, it looks perfect, right? So it's just when you add in that long wavelength filter that they could see that bifurcation. So, but it's tiny still.
I'm going to ask about the subarray transfer, which you have there. For nearest, we did the same thing, and we didn't get values that were as high as that. And the question is, are you going to try that again in the future to try and see if you can do better?
Yeah, we repeated that one in cycle 2, but we haven't looked at the cycle 2 data yet. The one that I showed is the cycle 1 data. So we'll sort through that and see if it gets any better. But some of it is that I think in cycle 1, we were trying to be as efficient as possible, and we didn't get as many dithers as we maybe should have. And so once we add in the new data, we'll get better numbers, I think.
Right, thank you.
I wanted to check, are there any online comments? No, okay. Any further comments? We have plenty of time, actually.
I'm a fast talker.
Yeah, thank you. You got us back on schedule.
Yeah.
I appreciate that. Okay, well, thank you, Martha. You can.
This works. Excellent. Now I can look at it.
So I will give you a 5.
Okay, thanks. Okay, continuing the theme, talking about calibration of web instruments, I'd like to talk about specifically the calibration of the Milli field unit spectrometer. Microphone? Turned off. Thank you. Before I talk to the next 10 minutes with nobody hearing me online. I'd like to talk about the calibration of the Milli IFU spectrometer and drill into details of how we calibrate it and some general lessons to take from it for calibration beyond Milli as well. So many folks here are probably familiar with, is this not working anymore? There we go. Many folks here are probably familiar with the IFU, but for anybody who isn't, this is a 4-channel integral field unit spectrometer in the mid-infrared. So we've got 4 IFUs all taking data at the same time in a concentric field. The shortest wavelength band is the smallest field of view. The longest wavelength band is the largest field of view. They each disperse data onto 2 detectors. And when we can reassemble things into data cubes, it gives us kind of a data pyramid of information. We've got 3 grating settings that gives you the first, middle, and third segments of each of those bands. When you put it all together, then you've got uninterrupted coverage from 5 through 28 microns at spectral resolution up to about 4,000 or so. So it gives us 12 bands that we need to calibrate individually, yet consistently with each other, because we'll end up putting them all together. The actual data looks like this. That figure on the left you're looking at there is a point source. Looks like a point source, doesn't it? The reason why you're seeing so many different traces is because you've got 2 different wavelength ranges, one on the left half of the detector, one on the right, and there's all of the individual slices. Multiple can be lit up by a single point source. They're all dispersed. That's where we do our calibration. We do that at the 2-dimensional detector stage, and then we put things together in the pipeline with a 3-dimensional version of the drizzle algorithm to build a data cube that looks like that thing on the right. So that looks a lot more like what you'd expect. You can see that it's a point source in this case, and you can do traditional aperture type photometry at each of those wavelength planes. So at each wavelength plane, you put an aperture around it, you do an annular background subtraction, make an aperture correction. You can stack that up into an extracted spectrum like we're looking at the bottom, in this case for a 09 star 10 lac. There's a lot of challenges to calibrating it. We heard about some of them this morning. Here's a list of just a few of them in here. We've obviously got issues with our flat fields. We can't use the internal lamps for various reasons, and there aren't a great number of sources on Sky for doing flat field calibration in the mid-infrared. We've got fringing because we're a mid-infrared instrument. We get reflections internal to our detectors, which put roughly 30% amplitude fringes on all of our data that we need to correct out in the pipeline. The default pipeline does a pretty good job, and there's some options in there that we make sure to turn on for all of our flux calibration work as well to calibrate any residual fringes. So that figure you're seeing down at the bottom left there, for instance, the blue line shows you the default that you get out. You can see that residual ringing in there from the fringing in the detectors. When we turn on the residual fringing step, then that ringing largely goes away, not entirely, but it goes to a low enough level that we can actually do the analysis we need to with the data. We've got time variable dot current at short wavelengths. We've got time variable thermal background at long wavelengths. We've got time variable throughput. And we've got aperture corrections that are discontinuous between the spectral bands because our pixel size changes. I could add BFE to this list as well, but instead for today, I'm going to ignore almost all of those effects and concentrate just on 2 of them, namely the thermal background and the time variable throughput. That last was an exciting discovery during cycle 1 operations of the instrument when we realized that if we observed a single source at multiple different times, the amount of electrons and dN per second it produced on the detector varied substantially. So if you look at, now pick your favorite calibration source in the sky, normalize that to 1 count rate at all wavelengths, that gives you the black line in the top left figure. If you then observe it a year later, so in now summer of 2023, suddenly it's producing half the number of counts that it used to at about 25 microns or so. It's continuing to go down, but it's slowing dramatically. So the red line underneath that shows what you get when you observe that source again a year later. It's a fairly smooth loss, but very pronounced at long wavelengths. The happy takeaway from that top right plot is that the rate of loss in the effective count rate is slowing dramatically over time. It seems to be either asymptoting or just declining ever more slowly as a function of time. So one of the things we had to do in the first year of operations was take lots of measurements from our internal calibration lamps and try and fit a functional form to how is the loss behaving as a function of time. So as part of our calibration process in the pipeline, I essentially use this model to back correct everything to the 0-day counts that we would have got in April of 2022. Once we make that correction, the actual stability of the instrument is now very good. So this is just showing you how now if we take a single standard star, we apply all of these corrections in the pipeline, then the repeatability at most wavelengths is sub% or so. At longer wavelengths, a little larger, maybe 2 to 4%, but there's no obvious systematic from the model that we're using, and this may just be because the signal to noise is lower in these bands that we're looking at instead. So as part of the overall FluxCal program that Carl was describing earlier, we also just published a paper on the MRS flux calibration, which you're welcome to go and read if you want more details. But the upshot is we observed about 10 or so stars, varying in type from O stars to A and G type stars. To make things a little more lively, we've also thrown asteroids and young stellar objects into the mix as well. Those turn out to actually be important by the time we get out to long wavelengths. This is the basic approach that we take for calibration. We use the stock AWST data pipeline for everything that we're doing. We process the data through the entire pipeline, leaving out only the step in which we apply a photometric correction. We're applying a time correction, but not the photometric correction. We apply some optional steps, the residual fringe correction I talked about, and auto-centroiding to make sure that we're actually locked on the correct aperture location for the stars, annular background subtraction, all that good stuff. Then we ratio the extracted spectrum in effectively flat-fielded dN per second to the CalSpec model and use that ratio as our calibration vector that we need to get things on an absolute reference frame. That's what I'm showing you here. The blue line there is what you get if you're looking at star 16 Cygnus B, a G star. The gray line is what you get if you look at 10 Lac, an O9 star. And you can see there's some noise in there, so we fit that ratio with a low-order basis spline model so that you can try and take out both some of the noise in the spectrum itself and some of the features from emission and absorption lines and things like that that we don't want to bias our models. You can see that 10 Lac is much higher signal to noise than 16 Cygnus B. Largely, it disappears behind the black line fit that you're looking at there. That's because we didn't observe this originally as a calibration star for FluxCal. We observed it for distortion calibration. So we actually had a 57-point dither where we moved it all around the field of view to calibrate our distortion solution. But it turns out it does great double duty as a flux calibration star as well. Particularly because we're moving it around so much, it marginalizes over a lot of flat field sins. You can also see that there's a spatial offset between the two. The calibration vector you get from 16 Sig B is quite different from what you get from 10 Lac, and that's a real effect. Different stars give different calibration vectors. So in order to move things onto some average for all of the stars, we observed all various different cal stars, O, A, and G type stars. We ratioed their calibration vectors against 10 Lac, and then did a low-order polynomial shift so that we could match that average response vector in the range of 5 to about 18 microns or so. You can see that things obviously kind of fall off fairly rapidly by the time you get above 20 microns or so. The individual measurements you get from stars aren't as good, and there's also a much larger spread in the calibration factors, and that's just because stars are getting quite faint by the time we get out there. So this is the issue that we're fighting against when we're working at 20 microns in the mid-infrared. Left axis is showing you the source flux density in Janskis. That orange line there is our 5th magnitude primary calibrator star, 10 Lac, and it's really diving down by the time you get out to long wavelengths. At the same time, the thermal background, the axis on the right, that is shooting up very rapidly by the time you get out longwards of 20 microns. Where they cross, you suddenly start getting much worse calibrations from even a 5th magnitude calibration star. And it becomes a lot less reliable. Issues to do with your background subtraction start to dominate your calibration instead. So what we really need in order to get a good long wavelength calibration is something that is much brighter at the mid-infrared 20 micron long wavelengths. So to keep things interesting, we've tossed an asteroid into the mix. The blue line there is the asteroid 515 Athalia, which is a factor of about 10 or so brighter at long wavelengths. Those jumps you're seeing in the spectrum, though, are real. Athalia is a variable source because, why make things easy? So actually, we use another source as well. That now young stellar object is shown in green, which is a wonderful source. It's almost 10 Janskys at 27 microns or so, which is exactly the kind of brightness we want to use in order to calibrate. So in a somewhat convoluted process, then what we do is we fit a black body model to Athalia, which, as I mentioned, is now rotating. So each of the segments is offset from one another. It's time variable on times of 10, 15 minutes or so between our different bands of observations. But we kind of adjust that all to some moderate level that we can fit a black body model. We get the relative response within each band to the fit to the black body model. Then we use the young stellar object, which we assume doesn't vary on 10 to 15 minute timescales, just to ensure that we've got the right absolute normalization of the overlaps between the bands. So we make sure absolute calibration on band 4A matches 3C, and then it matches 4B, 4C, et cetera. We use that to bootstrap the absolute calibration to go along with the relative calibration from the asteroid. It's not perfect, but it works a lot better than using stars for that so far. We would like to use stars for this going forward, though, so we're in the middle of looking for 0th magnitude stars that hopefully we can look at in future, which is exciting to be pointing Webb at 0th magnitude stars, but in mid-infrared, that's about as bright as you need in order to get really good signal. Cross-calibration against the MIRI imager looks really great. So this is comparing against all the work that Carl's been doing for the imager. Generally, if we do pseudo filter photometry from the MRS spectroscopy, we match the imager to within about 1% or so for the average of all the stars that we're looking at. We can also do calibration against external sources. So we compared point source photometry against the MIRI imager. It's also important to look at extended source photometry, where the differences in your aperture corrections become important. So we've actually been using giant planets in the solar system to try to check that we're doing the right thing with our extended source calibration. So we're comparing MRS observations of Saturn, for instance, in that plot there. We can make a map of the brightness temperature of Saturn and compare that to old Cassini measurements from a number of years ago, and find that the effective surface brightness temperature of Saturn is consistent with what we got from Cassini to within known seasonal variations. But actually, a tighter constraint is when we compare to Voyager data of Uranus, which was fun tossing a Voyager comparison into the FLUX Cal paper recently. We find that we're consistent with the flux calibration of Voyager to within about 0.4 Kelvin or so and get the same pattern of variations over the face of the planet. So this is a nice external check beyond the usual comparisons that we're doing the right thing both in terms of the point source regime and the extended source regime as well. There's some potential offsets we're seeing. This gets back to a plot that Carl showed earlier. Now I'm showing a slightly more controversial version of this plot, in which I'm showing that the two O stars that we've observed might be systematically offset from the calibration vectors that we're getting from the A and the G stars. Both 10 Lac and Mu Col are off by about 3-ish% compared to the other stars. It's a little hard to tell if this is necessarily real. We have 2 stars. It's a much lower number than we've been able to observe in the imager. But the imager also kind of puts together O stars and white dwarfs into a single hot star category. So possibly we need to split things out in future to decide if the O star models themselves actually don't quite match what we're getting from the other stars in some way. And the final thing I'll leave you with for today is a comment on the exciting things that you see when you point a telescope as powerful at Webb in a new wavelength regime and spend multiple hours looking at a 5th magnitude star. This is 10 Lac, a boring O9 star, one of the stars that defines the class. Turns out it has remarkably broad high ionization emission lines in it. Now, full width half max of a couple thousand kilometers a second, and emission in neon 5, neon 6, and oxygen 4. This puzzled us for a while looking at the data, why I had to patch over the 10 lax spectrum in certain wavelength regimes. We'd assumed it was some kind of a calibration systematic. But once you know the right questions to ask, you can drill in detail and realize it's not calibration systematics at all. It's the fact that there's some really exciting high ionization emission coming out of this star. And it looks like that might have an interesting scientific import as well, helping resolve something known as the weak wind problem for late type O stars. So word of warning, when observing things to depths you haven't done before in wavelength regimes that are relatively new, you might find exciting things that mean maybe a star's not quite so boring as you thought it might be before that. So I'll stop there, and thank you.
Thank you, David. Are there any questions for him? Yes. This is going to be.
Hi, David. Thank you. So exciting time variable instrument throughput. Do you know kind of what's driving that? Is that some kind of instrument degradation or contamination or combination of things?
It's a little difficult to say. We know certainly that there is some contribution from the dichroic elements in the maybe optical light path. So if I flip back to that, then yeah, so if you're looking at that plot on the left, the fact that you can see those discrete jumps between the individual bands, the only thing that changes there at fixed wavelength is which dichroic you've got in there for selecting the ranges. So that's telling us that there's some contribution from, I don't know if it's just a generic darkening or loss of throughput in the optical elements, but we can't say if that's the only effect, if there's also contributions from detector degradation. I wish I had a solid answer for you, but at the moment, I don't have a conclusive single statement.
Thank you.
I wanted to check online. Do we have any comments?
I'll just make a comment to point out that the imager also sees a degradation at the longer wavelengths, but smaller.
Yes.
And the imager does not have dichroics, so it can't just be those. So that's it. The answer is it's complicated, sadly.
Surprise.
Okay. Do we have any further questions? Yeah.
Well, I thought my talk was bleak. Yep. So I have a question for the last three speakers, and that is, here's flagship next-gen space telescope with three really different instruments with really different optical configurations, but they're all kind of bottoming out at this, pick a number, 1-2-3% level. And I'm just curious to know, do you folks have any sense of is there a common dominant contribution to the uncertainties here? Is it just coincidental? Because it's really quite interesting that they're all kind of at the same level. Is it commonality of detectors or what? Do you guys have a sense?
So I know certainly for the MRS at least, there's just a confluence of factors that all stack up by the time you get to the 1 to 2%-ish level. So now for us, for instance, the time correction for the throughput evolution, it's a phenomenological model we've fit through the observations that does a pretty good job. I don't know if I'd trust it to better than 1% or so at longer wavelengths. That's also the area at which you're starting to see the differences between calibration stars mattering. As you pointed out earlier, everything starts mattering once you get down to that 1 to 2% level. Going below that is incredibly hard.
My question was, and I may have missed it if it was in there. Have you done any explicit tests for nonlinearity?
Yeah, so there's a number of plots in the paper I linked to that I didn't add into the talk today, but we've tried looking for things like nonlinearity for how well you fill up the the well depth, the absolute brightness of the star, etc. Those don't show anything particularly obvious. But there are certainly going to be some low-level effects. Again, at the sub 1% level, our linearity is not great. We don't make a correction for the brighter, fatter effect, which we certainly see in the data. And those are things that we're trying to looking at optimizing going forward. Yeah.
I think we have time for one more question. Is there anyone else? Okay.
Thanks. So I guess I just thought I would ask, I saw that with the asteroid you mentioned, I believe that was part of a program to avoid using something like a residual fringe step to attempt to divide out the relative response function. I guess I'm just curious, is the pointing accuracy good enough that that's advised to avoid, fringing out or, removing your fringes and your spectral lines and instead just observe a calibrator as part of your observation?
Yeah, so to give context to everybody else, the process I talked about applying a residual fringe correction is essentially a Fourier-based technique. Look for fringes and known frequencies and subtract them out of the data, which works great when you're looking at a star and works very poorly when you're looking at something with lots of molecular features in the data that you don't want to remove. So there's been interest from a number of teams in using things with boring spectra like asteroids as fringe-type calibrators. And when you use target acquisition, that can work pretty well in general. You can generally lock things into the right location on the detector so that you can try to make empirical corrections. And now that team in particular I know has been having fairly good luck with using asteroids as calibrators for things like that. It's not necessarily so easy for absolute flux calibration, of course, because the sources themselves are variable, but for fringe removal, it can work well. And one of the things that we're exploring at the moment with some calibration programs in cycles 2 and 3 is taking bright stars, 10 lakh in fact, and rastering it around a grid point of patterns around the normal dither positions to see if we can actually make a library of such fringe corrections for point sources, so that in future cycles, maybe you don't need to take those calibrations at all. You don't need to use our Fourier-based flux fringe correction, and instead it can just pull from that library. How well that works is still a matter of debate, but it's something that we're actively exploring so that you don't have to take that calibration time each time.
Thank you. Let's thank David one more time.
Thanks.
Organizers, would you like to see the discussion session?
Yeah, all over.
Okay, yeah, maybe 20
minutes?
half an hour. Yeah, we have 30 minutes.
Big bags.
We have our discussion session. One of the topics proposed by George Lee was how to achieve best uniform calibration across past, present, future astronomy projects. So I don't have voice, so I will leave him to moderate the discussion.
Okay, so the thought behind this is you've seen wonderful progress, 1% sort of errors in calibration with JWST. It's a big advance. And so I was wondering if we could think of establishing a baseline calibration that could be used across all of astronomy. And that's a very complicated thing. It sounds easy, but I mean, it's something that could be used by somebody on a 24-inch telescope doing a master's thesis all the way up to huge ground-based telescopes, including JWST. And there are a bunch of different problems. But if we could do it, it would be a major advance because then everything would be on a consistent absolute calibration scale. So that's the discussion topic. And it's not supposed to be a speech. It's supposed to be a discussion. So what do people think?
So are you proposing that there's to establish a set of sources to use?
So part of this for modest-sized ground-based telescopes would be to have a dense network of stars that were well calibrated. For example, in the infrared, the extended WISE mission could provide you with a dense network of stars. Two mass has sort of 2% errors over the whole sky, but for this purpose, it's not bad. And the individual errors are not great, but if you did a number of 2-mass stars, in the optical, I think white dwarfs have been widely used. I'm really not acquainted with how useful that is as sort of a general solution, but on the other hand, I learned during the coffee break that large telescopes are using up-looking radiometers to get the extinction, and that just emphasizes that there isn't a single approach that will fit all, even on ground-based telescopes.
So I have a couple of things to ask about. What wavelength range are we talking about here? Are we going to try to go into the ultraviolet? Are we going to just optical the infrared? And the second thing is, a lot of the stuff we're doing is very fundamentally dependent on the Hubble Space Telescope, which is, of course, wonderful, but how do we relate that to ground-based observations in a specific way? Because the atmosphere is doing all sorts of bad things for us all the time. And in the first talk, it was a mention of one case where you had an actual dedicated telescope looking at the atmosphere along with your telescope that's looking at your source, which is wonderful, but that's not generally the case. And for almost everywhere else, you're going to have to try to somehow a posteriori figure out what your atmosphere is doing. And that's really difficult.
So I'm not guaranteeing that all observations would be accurate to 2%. I'm saying the baseline would be accurate to 2%. And then the product you got would depend on your observing platform, atmospheric conditions, whether you were a competent or incompetent observer. There are a lot of variables. But I don't think that what we're doing now is subject to space versus ground. It's all the same problem. And we ought to view it as one problem. And the question is there a uniform solution that could be applied that way? I think, viewing calibration as a Hubble problem or a JWST problem is not the way I would look at it. And I would think you would at least want to do it from near ultraviolet out to 20 microns, longest wavelength of ground-based infrared. And then there's a detector change beyond that, which you might not want to take on.
So I wasn't trying to separate into space and ground in the beginning, but of course you do have those two groups of telescopes that are going to be using this, and that's what introduces this dichotomy that you have to worry about, in my view.
No, we have another microphone that we can use maybe. Swap.
This better? Okay.
Is there another? Is that one working? They work.
This one works. All we need is one for now. Any more comments?
Yeah, I have a comment now that I'm fighting over the microphone.
Got one.
There you go.
Yeah.
Oh,
I know.
so I agree with your, actually, I could sit down. I'd rather stand up. With your comment and disagree with yours that it's a dichotomy between ground and space. So I agree with yours, but I don't know that you can have one source to rule them all over all.
No.
That's not ever going to happen.
Can we all agree not to have one?
I thought I was trying to get across that we need many.
Yes.
Yes, that's absolutely true.
We need many. That covers the entire wavelength range. And you may have to do a little daisy chain.
Yeah.
In that this one over here is not going to be good for the UV, and this one might not be good for 30. But I think we have to do them all. And the atmosphere is an issue, but
yeah,
we know how to deal with that. We make measurements.
I think Susanna has just plunged right into the fundamental issue here. I mean, for example, the white dwarfs that have been developed and are used with HST extensively are have very few observations from the ground because they tend to be too faint and they're not distributed over the sky and et cetera, et cetera. So that just says there has to be a transfer to a whole bunch of other sources.
Hi, right here. So FLUX calibration, not my field. I work in.
Say your name.
Oh, I'm sorry. My name is Erica Egan. I'm at the Johns Hopkins Applied Physics Lab. I'm an exoplanet astronomer, so I'm used to very, very nice, precise relative photometry measurements and spectroscopy measurements. So this is not my area of expertise. So this might be a question of a very beginner question. But from what I understand and I've gleaned from this morning so far is that a lot of the sources of error come from, a bunch of tiny instrumental effects, very, very complicated things on the pixel level, on the detector level, on not well constrained throughputs of the instrument down to the level that we would like, but also, perhaps small time variable effects over, days, weeks, or months between observations, if extinction is changing, if the atmosphere is changing. And I'm wondering if there's ever been a campaign to get as many observatories, both on the ground and in space, to observe the same target at the same time, or at least at the same, period of time. So that way, that amongst those observations, the thing that they all have in common is the stellar signature. And would that enable you to sort of back out? We know exactly what the star should be because we have all of these other instruments that are observing it and sort of doing this comparative measurement. Would that be something that could help us beat down and get below that 1% flux calibration that we're interested in?
Microphones.
Let me get one.
Hey, my name is Misha. I think that I get the point what you're suggesting, but the problem here is that you need to calibrate the atmosphere, and that's probably might even be a bigger obstacle than calibrating detectors. Talking about observing the same source with many different observatories at the same time.
So, Justin?
So, is this on?
Yeah, it's on. It was on.
If you have a source or set of sources that you're treating as, or want to treat as a fundamental standard, it would at least be nice if they were SI traceable themselves. But where you're going to, if you treat anything natural in the sky, that is and you put it on an SI scale at time t, where you're going to break the chain is if you make any assumptions about what its brightness is at any other time, because these are all complicated objects that change. They're all time dependent. Need to keep that in mind. Ultimately, over the centuries, the coming centuries, it would be nice that, if we move more toward artificial sources, because there you can calibrate them in the lab SI traceably, and even sometimes if you can get them back, then you can calibrate them after they've been in space again, and you don't break the chain at least as much as with a natural source.
I have one comment to that, which is that we can't always be building these SI traceable artificial stars. And the nice thing about natural stars, they're there. You don't have to build them. They're even green. They're naturally powered.
I think Elon Musk is going to a lot of.
So I'm gonna posit that one of the things that we need by not having one primary standard, but by developing a whole system of standards, is that you can then have a natural star where you need it, when you need it to do your calibration.
So I think there's some confusion in the discussion. I think it's not practical to do this to 0.1%. I think it would be practical and be very helpful to do this to the 1.5% level, which I think is what we ought to focus on discussing. But we don't even know how to get to 0.1% in dedicated observations. So imagining a sky network that was that good is a little premature. Okay, comment.
So again, not from the new to the community, but I see different presentation that show the different. I see different words: absolute flux calibration, and I ask myself, as someone who's been like getting ready for this conference for some time, I don't even see a unifying definition. I don't see a trace. I don't see a line that draws a logic. And coming from the heliophysics division, and as other people who had some experiences, we had that case in which a community thinks they they got the reins on something, and then comes the first kind of empirical test that kind of changed things. So SIM would be a good example. So is there an effort in the community before going to the next step of creating a standard network of stars to establish what does this set of words mean for us? Absolute flux calibration or uncertainty, because it's very hard for me to nail down, like, are you talking about the same thing? Is this because this is telescope X and this is Y? So maybe you can bring some clarity. I'm sorry for my long question.
Well, so I think what this would take is a sort of continuation of what Carl described that we did for JWST, where we came up with 3 different calibration types, and we had a lot of discussion about different approaches and so on. I think you'd have to basically have a group of people that sat down and evaluated different candidates. I think they have to be stars for this to work. Decided what would be a suitable kind of object. I mean, if you're going to use WISE stars, there's a wide range of spectral types, for example. You have to decide what you will focus on. And then there would have to be some sort of report that would come out of this with recommended calibration procedures. I think that's, it would be some procedure like that would be required to set this up. So I don't think it's trivial as sort of asking Ralph to tell us what to do is probably a good start, but it's not going to be the end.
Hi, up here in the corner. I'm Brian Kloppenberg. I'm the new director of the AVSO. So we've dealt with a lot of these flux calibration problems for many, many years, having done ground-based photometry with amateur astronomers. There are a variety of calibration fields. Landau is probably the best reference for those that exist all around the sky. Granted, they're not overall wavelengths, but some of these do exist, so there is some precedence that we could build upon. We've also done like global individual telescope level observing campaigns, and we found that even amateur astronomers are capable of delivering really good high quality data at kind of this 1% internal error, ignoring the catalogs because they have pretty large errors themselves. So I think it is quite possible to build these types of catalogs like what you were discussing. And I would say that I'll be talking more about this on Thursday, but I will say that if there were like a calibration source or like some standards that we could use, it would be really helpful for us.
So I'm very curious in this context of the baseline calibration right across. I want to start FUV all the way to mid-infrared. So in selecting this master sample of, what did you call them, main stars? I'm curious, is anyone concerned about the accuracy of the models themselves? Right? That hasn't been mentioned. And so I was getting like very positive, like, oh, that's not a concern. But how accurate are the models, right? So we know Ralph and collaborators, they work on the HST primary standard stars. And those, they've gotten very, very far. But as you expand outside of those stars, how are the models? Are they reliable? I mean, we should have theoreticians here. What are we missing on the modeling side?
Well, my own opinion on that is that if we pick the spectral types of the stars that we're modeling, we understand them well enough that the 1% level, we can probably carry this off. And that by 1%, I mean sort of from visible through the infrared.
I mean, my addendum to comment to that is I think the models are good on average, but not for a specific star. And I think that's the key. I think one of the things we need enough stars that you can average over the differences between the models, the average models for that kind of star, and the fact that each star is unique. And I think this gets to your question, Chris. I think this may be where our limitation is right now and why we're limited by 1% or so, is that stars are just not exactly the same. And we don't have NIST calibrated measurements at all the wavelengths we need. That's, I think, one of the keys. If we had measurements of the stars for this full spectral range, something that was traced to black bodies, etc., right, then we wouldn't have to worry about the model. We'd have to worry about variability. That's a separate thing we can worry about, right? But we don't. So we have to have the models are a real key part of the uncertainty budget.
Now, then we'd have to worry about getting the funding to get all those measurements.
There was.
So here's what
real
worries
quick.
me.
It's just my last slide in my next talk. I'll address that question. Show you something that's kind of scary. If you're.
So here's what worries me about what Carl just said, and that is if there is object by object variation between the models and the observations, and that is surely a lower bound on the systematic error of these models, right? And George's point is it's okay to 1%. I'd certainly be in favor of us extending the CalSpec idea of establishing a network of spectrophotometric standards from, DC to gamma rays across the entire astronomical spectrum at a range of magnitudes. That'd be great. But I think we should be very sensitive to the fact that it is extremely dependent on our aspiration of having understood stellar atmosphere models, right? And I really worry about what you said, because again, I think that's like a lower bound. And so just kind of a cautionary note here that in case you can't tell, I have a lot of apprehensions about pushing these model-based calibration methodologies into regimes where they haven't really been demonstrated to be valid. And it may well be one of the things that we're bottoming out on.
And then I guess I also just had a question because I'm also new to this, but
Can you say your name?
Sorry, my name is Maria Jose, justamente. And I had a question regarding maybe this is relative to specific wavelengths or whatnot, but I was wondering, which systematic should you push more, right? Like, is this scatter between models big enough compared to other systematics in such a way that it's irrelevant for us, to drill deeper there or not? Like, I mean, maybe you guys know the answer to this, but I guess I don't understand the magnitude between the different systematics that one should drill in at different wavelengths. Like, for instance, considering like with Earth telescopes, right? Like if atmospheric changes are big enough, that doesn't matter. To give an example.
And then Morgan.
I'll address some of these things on the last day in my talk. But I think the main point is that it's possible to test whether the atmospheres produce enough if you design an experiment, try to do that. That's what I would address.
Florian Kerber from ESO. I think it would be very attractive to have a dense network of many standard stars or reference stars across the sky. I think what it also requires is a major investment, right? I mean, having a working group of some people bringing down the guidelines, more than happy to start the discussion during the workshop, but you will need to have a major commitment from all of the players because it will be a multi-year effort. And to sustain that effort, that is really something that you need to have the commitment. Otherwise, I suggest it's a lost cause. And then just another comment on the comparison between observatories. You can definitely do this, look at the same star, but for ground-based observatories, you need to have quite a bit of equipment to actually characterize the atmosphere above you. It's not just a telescope.
A comment. There's a whole fleet of weather observation and Earth observation satellites. And I'm reading this off my phone because it's non-astronomical lingo. So the World Meteorological Organization and the Coordination Group for Meteorological Satellites, they established the Global Space-Based Intercalibration System, and that employs targets on Earth, deserts, ice shields, but also the sun, the moon, and explicitly stars. So when we are about to establish this thing, the system, this reference system, I think this is a group of people that we should include. They will be very interested in this.
I just wanted to make a comment on two comments. One is, I agree with you. It's a huge amount of effort. Having done this for JWST, it was a huge amount of effort, and it involved a lot of discussion to actually hammer out agreement. That's my one comment. And the other comment is, you're right to be skeptical of stellar atmosphere models. Is there any way to get around them for the wavelength range, the broad wavelength range we need, right? From a practical standpoint, what else do we use?
So I would, in my NIST way, I would say the models are great as transfer standards, but you still have
Absolutely.
to the measurements.
But we have such few measurements.
Well,
And I know we're changing that, but we have such few measurements that it's hard.
well, there's a sequence here, which I think we may be losing a little bit. There's a very small number of stars that we can actually get accurate absolute calibration measurements of, and even fewer we can get over a broad spectral range. There's a larger number of stars that we can do atmospheric models we think are pretty good, so we can extend it to them. And then there are lots and lots of stars that would be very useful if they were simply measured relative to the calibrated stars in a uniform way. And I think for many observations, that would be a helpful result, which might not involve quite as much work as you're saying. I mean, there are various levels of accuracy and so on that need to be discussed along these stages.
Yeah, John Woodward from NIST. It would be useful for us to know what densities at what wavelengths would you want to have measurements at that would allow you to compare different instruments. How fine resolution would you need on a spectrum to be able to compare passbands that are different from instrument to instrument? I'm not expecting an answer, but I think it would be a topic for conversation.
Jamie Tyre, University of Florida. One thing I want us to remember is that there are people taking millions of high resolution spectra with the same instrument for a wide variety of stars. Now, they're not absolute calibrated in the same way, but you could imagine if we could link into a system like that, you can at least see the relative variation star to star for the same sort of star, and maybe kind of address how much worry you have for the modeling on that side. And then also consider whether there's a way to link them into the standards such that, you get some relative variation that's already on some scale, if you could calibrate that scale.
So speaking of high resolution, so I did the FLUX calibrated kick high res, and compared to the G191, which is a model, which is very different. So I have to tell you, model is not quite matching to the best observations. It's worrisome.
So just to go back to your talk this morning, you mentioned the sun being the best calibrated thing we've got over a wide wavelength range, I think. Absolutely. Right. So we should think about whether we can then take that, and there's been a lot of work on solar analogs that may be one way to start off on this process of getting many more sources that we can accurately produce some kind of description of that for our needs.
Yeah, I think some people would argue that white dwarfs are understood better than the sun, right? But I think basically that's what we need to, that's what we would need to do is pick some things we thought we really understood and then work out from there to expand. But let's not forget that there's also the point of providing a means to transfer to a much larger sample of stars that are useful as secondary, tertiary calibrators that are not modeled in detail. But I think that would be useful for many kinds of observation. It's a little bit like your standard field calibration stars, except over the whole sky. I think they may be getting hungry, Susanna. So let me try a summary. I think there's some interest in this. It sounds great in half an hour discussion. It might not sound so great after one really got into the details of what was involved. But I would suggest that we ought to continue discussing how to take steps toward this. As I think everyone would agree that the farther we could get toward this goal, and if we never reach it, better off we know what would be a useful skywide network of stars. How do we transfer? I think all those things ought to be taken into consideration. And we have at some level done a lot of calibration in the past, mission by mission and need by need. I think it'd be useful to get over that and do it with a little. If anyone disagrees, raise your hand. Okay, I think it's time for lunch.
Thank you, everybody, participating to the discussion. Lunch is available now in the cafeteria, already said that. So we have plenty on Slack, but it will be available on paper also at the registration desk. It's a signed sheet with some potential discussion topics for the next session. Please vote your favorite 3 topics. So put your name there. You don't need to put your email, just your name. And then we will decide, what topic to cover in the next sessions. Do it now at the lunch break if you can, but as soon as possible. So since the first discussion slot, the second one actually, will be at 4:30 this afternoon. Thank you and see you at 1:30.